Computer science represents one of the most transformative and intellectually dynamic fields of human endeavor, fundamentally encompassing the systematic study of algorithmic processes, computational machines, and computation itself across theoretical foundations, practical applications, and experimental implementations that collectively form the bedrock of our digital civilization. At its conceptual core, computer science is not merely about programming or computer hardware, but rather investigates what problems can be computationally solved, how efficiently they can be solved, and what architectures can execute these solutions, spanning an extraordinary spectrum from abstract mathematical theory to tangible engineering applications that have reshaped every facet of modern society. The discipline's theoretical foundations rest upon several pillars, including the formalization of computation through automata theory and Turing machines, which establish the fundamental limits of what is computable, the mathematical study of algorithms, which analyzes their correctness and computational complexity in terms of time and space requirements, the principles of information theory, which quantify information and channel capacity, and the logical foundations underpinning programming languages and system verification. These theoretical constructs provide the rigorous framework upon which all practical computing systems are built, establishing boundaries for computational possibility and impossibility that guide technological development while continuing to inspire profound philosophical questions about the nature of mind, intelligence, and the universe itself as a computational system. The architectural dimension of computer science manifests through computer organization and architecture, which translates abstract computational models into physical systems through hierarchical layers including digital logic circuits that implement Boolean algebra through gates and flip-flops, microarchitecture that orchestrates data paths and control units, instruction set architecture that defines the machine interface, operating systems that manage hardware resources and provide services to applications, and compilers that translate high-level programming languages into executable machine code. This multi-layered abstraction enables the miraculous complexity of modern computing while maintaining conceptual manageability, allowing specialists to work at appropriate levels of detail without requiring exhaustive knowledge of underlying implementations. The software engineering dimension addresses the systematic construction of reliable, maintainable software systems through requirements, analysis, architectural design, implementation methodologies, testing protocols, and maintenance practices that collectively transform computational possibilities into practical applications serving human needs. This domain has evolved from individual programming artistry to disciplined team-based processes employing agile methodologies, version control systems, continuous integration, and sophisticated debugging tools that enable the creation of systems comprising millions of lines of code that nevertheless maintain coherence and reliability under constant modification. The data management sphere encompasses database systems that provide efficient, reliable, and secure storage and retrieval of structured information through relational models, query languages like SQL, transaction processing, and distributed database architectures that ensure consistency, availability, and partition tolerance in networked environments. This domain has expanded to include big data technologies that process massive datasets across distributed clusters, data mining techniques that extract patterns and knowledge, and information retrieval systems that power search engines and recommendation systems which have become indispensable to modern information economies. The artificial intelligence branch explores the creation of systems that exhibit behaviors associated with human intelligence, including learning, reasoning, problem-solving, perception, and language understanding, through approaches ranging from symbolic logic and expert systems to statistical machine learning and neural networks, with deep learning architectures now achieving human competitive performance in domains like image recognition, natural language processing, and strategic game playing. This rapidly advancing frontier raises profound technical challenges in scaling, interpretability, and safety while simultaneously generating urgent ethical questions about automation, bias, privacy, and the future relationship between human and machine intelligence. The networking and distributed systems domain addresses how computational entities communicate and coordinate across physical and logical boundaries, encompassing Internet protocols that enable global connectivity, distributed algorithms that maintain consistency without central coordination, cloud computing architectures that deliver scalable resources as services, and cybersecurity mechanisms that protect systems against malicious actors through cryptography, access control, and intrusion detection. This interconnected fabric has fundamentally transformed human society by enabling instantaneous global communication, collaborative creation, and unprecedented access to information, while introducing novel vulnerabilities and governance challenges that computer scientists continue to address through technical innovations and policy recommendations. The human-computer interaction specialization focuses on designing interfaces that bridge human capabilities and computational power through user-centered design methodologies, usability testing, accessibility standards, and visualization techniques that make complex data comprehensible, ensuring technology serves human needs rather than forcing human adaptation to technological constraints. The programming languages subfield develops formal notations for expressing computational processes, studying their syntax, semantics, type systems, and implementation techniques across paradigms including imperative, functional, logical, and object-oriented approaches that offer different conceptual frameworks for problem decomposition and solution structuring. This theoretical work directly influences practical language design, with modern languages incorporating sophisticated type inference, memory management, concurrency models, and domain-specific capabilities that enhance programmer productivity and software reliability. The scientific computing application area develops computational methods for solving problems in science and engineering through numerical analysis, simulation techniques, and high-performance computing systems that model physical phenomena from molecular interactions to galactic evolution, enabling discoveries that would be impossible through traditional theoretical and experimental approaches alone. The educational mission of computer science cultivates computational thinking, a problem-solving approach that draws on concepts fundamental to computing, including abstraction through layered representations, algorithmic design through precise step-by-step procedures, decomposition through divide and conquer strategies, and pattern recognition through similarity detection and generalization. This mindset has proven valuable far beyond traditional computing applications, influencing disciplines from biology to linguistics, by providing frameworks for managing complexity and building systematic solutions to multifaceted problems. The societal impact of computer science continues to accelerate through emerging technologies, including quantum computing, with its potential to solve currently intractable problems, ubiquitous computing that embeds processing throughout our environment, bioinformatics that applies computational techniques to biological data, and computational sustainability that optimizes resource usage for environmental preservation. As a discipline, computer science remains uniquely positioned between mathematics, with its emphasis on formal proof, engineering with its focus on practical construction, and natural science with its empirical investigation of computational phenomena, creating a rich interdisciplinary tapestry that both draws from and contributes to numerous fields. The historical trajectory has moved from theoretical foundations in the 1930s-40s through hardware development in the 1950s-60s, software methodologies in the 1970s-80s, networking expansion in the 1990s, and data-intensive applications in the 2000s toward our current era of intelligent systems and pervasive connectivity. Throughout this evolution, core questions persist about the nature of information, the limits of computation, and the most effective ways to structure complex systems, ensuring computer science remains a vibrant, self-reflective field that continuously re-examines its own foundations while expanding its applications. As computational technology becomes increasingly woven into the fabric of human existence, the principles and practices of computer science provide essential understanding for navigating our created digital world, while offering powerful tools for addressing humanity's most pressing challenges through systematic, scalable, intelligent solutions that extend our cognitive capabilities, much as mechanical inventions extended our physical capacities during the Industrial Revolution, establishing computer science not merely as a technical discipline, but as a fundamental domain of human knowledge that illuminates the very process of problem-solving itself.